Okay, welcome to the review on Chapter 17, Additional Aspects of Equilibria. Make sure you have a piece of paper, pencil, something to write with, and periodic table available. 3 sections, Chapter 17, Common Ion Effect and Buffers, Part 2, Titrations, Part 3, Solubility, Equilibria, also known as KSP. If you haven't watched the other review podcasts or videocasts before this, don't watch this one. You need a good background before you can hit this one. So go back to 15 and 16 if you haven't watched them, then tackle this animal. First part, common ion effect. We're going to buzz through some notes on these 3 areas really quick, not do a lot of sample problems because I've got a lot of AP questions to work through at the end as well. Common ion effect says that when you have an equilibria, you add an ion that is in common with that equilibria. So for example, here's an equilibria with a weak acid, HCN. If we add some KCN, which is this soluble salt, of course, because it's got potassium in it, it will dissociate, forming K plus and CN minus. This CN minus from this salt will be in common with the CN minus in the equilibria written up above. It will be in common with this CN right here. According to Le Chatelier's principle, then, the reaction will shift to the left because we've stressed the system by adding some of this ion to it. We will reduce the products' concentrations. Remember, Le Chatelier's principle says that if you stress the system, it will adjust to reduce the stress. And the way that we stress the system here is by adding some of this ion in common with it, and it should shove to the left, making the K, in this case a Ka of it, lower, or reducing the Ka, reducing the ionization of this particular acid. You can calculate this using an ice table, and we'll do some of this in a little while as well. But just knowing it qualitatively is very important as well. Also in Part 1 are things called buffers. Buffers are a weak acid or a weak base and a salt containing their conjugate. A weak acid or base and the conjugate base or the conjugate acid of that weak base or acid. Notice it has to be a weak acid or base. That's because both things have to be available, the acid and the base in the solution. Here's an example. Let's say that we have a 0.1 molar solution of HF, and we also have a 0.1 molar solution of NaF. We mix the two together. And let's say it ends up still having this same concentration after we mixed it. Well, initially then we'd have 0.1 molar here and 0.1 molar here. None of this, none of this. We could find out what the pH of this solution is, or we could go and use this solution to buff the addition of an acid or a base to the solution. Finding the pH, you could use an ice table here and do lose X, gain X, end up with 0.1 minus X, 0.1 plus X, ignore these X's, and then run it in through the Ka of HF. Or you could use something called the Henry-Hasselbalch equation. The Henry-Hasselbalch equation is designed to find the pH or the pOH of a buffer straight away, as long as you know the concentrations of the acid and its conjugate base or the base and its conjugate acid. You already ignore these X's, and that's what this equation allows you to do. Notice it uses the pKa or the pKb in these equations. One interesting question lots of times is how a buffer actually buffs, and writing the equation for that is sometimes tricky as well. Let's say we had this buffer solution right here, and we added to it some HCl. What equation would occur? Well, the HCl is an acid, right? A good source of H pluses. What in this equilibria right here would be good at reacting with H pluses? Well, the conjugate base, of course. So it would react with the F minuses in here, and we would actually reduce or remove some of these from the solution, adjusting the pH just slightly. Because if you look at it, the base right here is actually the logarithm of the base over the acid. So even though we add some strong acid to it, as long as it's not too much, we're not going to change the pH very much of that solution. Now, what happens if we added a strong base to it, like let's say NaOH? Well, NaOH, remember, is a good source of OH minus ions. What thing inside of this buffer solution would be good at reacting with OHs? Well, of course, an acid. And so HF would react with the OH minus, using up or removing some of this HF from the buffer solution. We wouldn't change the pH too much, though, because remember, it's the logarithm of the base acid ratio that actually would change the pH. Notice if the base and acid ratio is equal to 1, the log of 1 is 0, and therefore the pH is equal to the pKa, or the pOH is equal to the pKb. That occurs a number of times. It's a good choice, actually, if you need to know what substances to use to make a buffer of a particular pH. Choose one whose pKa is close to it, and then just make them equal concentrations. All right, next section, titrations. Titrations occur in a number of different ways. They can be an addition of a strong acid to a strong base, weak acid to a strong base, strong acid to a weak base, weak and weak, polyprotic acid to a strong or a weak base. We wanted to monitor the pH during the addition of the acid or the base, and we create titration curves. Interesting areas during these titration curves is if we start as an acidic solution and go up and reach a really big peak and then flatten out, are the area of most buffering. That's halfway to the equivalence point, because in this area we have lots of the acid and lots of its conjugate base available. And remember, an acid conjugate base pair is a buffer solution. Right here is known as the equivalence point. It's the middle of the steepest part of the curve. Right in the middle of that, the pH might be close to 7. If it's a strong acid and strong base, it will for sure be equal to 7. If it's a weak acid or a weak base, then you won't know for sure. You won't know for sure. You've got to know what's actually being added. The equivalence point, though, means that there are equal moles of acid and base. Equal moles. Notice I said not molarity, but moles. When in doubt in a titration, always convert to moles. Don't stay in molarity. Always convert to moles for your calculation. And then the area of excess base would be right up here. If the titration were in reverse and we were adding a base to an acid, obviously the curve would start here, go down and go this way. This would be our area of most buffering equivalence point here, and then this would be the area where the acid actually takes over most of the pH determination. We'll do some calculations with that in a little bit. The third part of Chapter 17 is solubility equilibria, also known as KSP. Solubility equilibria is the equilibrium of salts that don't technically dissolve. We memorized some solubility rules earlier this year and last year. Those solubility rules tell you which things really do dissolve a lot. Everything else has a KSP because it only dissolves a tiny bit. And this tiny bit is told to us about the solubility equilibria. So for example, here's CaF2. CaF2 is an insoluble salt according to the solubility rules. But I draw a double arrow here, and we get a little bit of this and a little bit of this. And I could write the K, or equilibria constant expression for this. The K for this would be products to the power of their coefficients divided by reactants. And of course, the reactants is a pure solid, so we don't put it into the expression. That's the KSP expression. Solving for KSP on these, or solving for what's known as the molar solubility, which is the concentration right here. You need a nice table. Plug and chug it in there. Watch the stoichiometry, because when you do x's in here, you'd get x amount of this and 2x amount of this. So when you put it in here, you'd end up squaring the 2 and the x. And when you put the x in here, you end up just leaving the x by itself. So be careful of the stoichiometry when you're doing those solubility problems. Common ion effect is still a possibility. So let's say we had this solubility equilibria right here and we added some NaF to it. NaF would dissolve because it's got a positive cation that's soluble, and we get some F minus. The F minus, of course, would be in concert or in common with the F minus in the CaF2, and so it would drive the equilibria to the left and therefore reduce the amount of F minus and Ca that is soluble. It would overall reduce the solubility. Knowing qualitatively that that would happen is just as important as being able to quantitatively determine it. pH can affect solubility. For example, in our CaF2 that we have right here, if we dissolve it in an acidic solution, like say for instance it's being dissolved in 0.1 molar HCl, the solution has lots of H pluses around. The H pluses will want to go and react with an ion that could form a weak acid. Remember, weak acids want to stick together really well, and so the H pluses would come and glom onto the Fs and form HF, in effect removing this from solution. And according to Le Chatelier's principle, if we remove something from a solution, it will adjust to reduce that stress. And in this case, it will adjust by shifting to the right and dissolving more. So CaF2 would be more soluble in an acidic solution than it would in pure water. You should be able to determine this qualitatively. And you can look at the numbers too. We'll look at it quantitatively. It doesn't show up that much. Make sure you apply Le Chatelier's principle to those ideas, a common ion effect and or acidic or basic solution. There are some strangers we should look at. Stranger things that form what are called complex ions, also known as ligands or coordinated complexes. Here's a couple of examples. Let's say that we had silver ion in solution and we added some ammonia to it. Silver, positive one, can act as a Lewis acid. It can accept electrons. Well, ammonia right here is a good electron donor, which is known as a Lewis base. And it forms this complex ion over here with a +1 charge. Aluminum does a similar thing. Aluminum's okay at accepting this extra hydroxide right here, and it forms AlOH4-. Now, you might not have to write the equation for this, but they might ask you, what does the charge end up being? Just figure out the charge the way you normally would. Silver's +1, ammonia's got a 0 charge, so the overall thing is a +1. Aluminum's +3, hydroxides are -1, there's 4 of them, overall -1 charge. Okay? These complex ions are unusual, but you should know that they exist, and you should know the strange names that they give to them. Lastly, questions about will a precipitate form? When you pour through two things together, will it precipitate, form, or not? Well, you have to find something called Q, and we talked about Q back in chapter 15. Once you find Q, you compare it to KSP, and you say, is it bigger or smaller? And obviously, when you reach KSP, you're right at that point where you can form a precipitate. So I always think writing the equation is the most difficult part for this. We'll work one sample problem on the next page here. You can write this down and then follow along with it. We're going to take 0.1 liters of 8 times 10 to the -3rd molar PbNO32, and we're going to take 0.4 liters of 5 times 10 to the -3rd molar Na2SO4, and we're going to mix them together. And we're going to ask the question, will a precipitate form? Will a precipitate form? We're given some additional information that the KSP of PbSO4 is 6 times 10 to the -7th. Lots of times the KSP that they give you is a huge hint as to what kind of equation you should write. Lots of times the KSP that they give you is a huge hint to the equation you should write. Now they try to confound you by giving you 2 or 3 KSPs, but you can usually figure it out. Take a look at these two and ask what thing would form a precipitate from this? Well, Pb and SO4 would form PbSO4, which is insoluble, but Na and NO3 would not, right? Because they'd remain dissolved. So your equation is going to be the PbSO4 precipitate that you're going to want to know if it forms or not, which will form the Pb +2 plus the SO4 2- ion. And I could write the KSP expression for this by saying that it is equal to Pb posi 2 to the first power times SO4 2- to the first power. Okay? Now, I need to know the concentrations of these things. Once I find the concentrations of it, I can plug it into this expression right here and find out if this expression is bigger or smaller than 6 times 10 to the -7th. Let's do that really quick. So the the concentration of Pb +2 ions in here is once these two solutions are mixed, notice it's a 0.1 liter and a 0.4 liter, would be equal to the moles of Pb +2 that are in there divided by my total number of liters. And my total number of liters is 0.5. The concentration of SO2- in there is my moles of SO4 2- in there divided by my total number of liters. And once again, it is 0.1 liters plus 0.4 liters or 0.5 liters. Just to make it a little bit quicker here, it turns out the moles of PB in there are 8 times 10 to the negative 4th. And the number of moles of SO4 in there are 2 times 10 to the negative 3rd. Doing the division right there, we end up with PB's ion concentration to be 1.6 times 10 to the negative 3rd, and SO4's concentration end up being 4 times 10 to the negative 3rd. Take these two critters now and plug it into the Q expression. Q would be equal to PB plus 2 times SO4 2 minus, both to the first power. When I multiply those guys together, I end up with a Q of 6.4 times 10 to the negative 6th. That's Q. Now, I need to compare that to KSP up here. Here's how to do that. KSP is equal to 6.3 times 10 to the negative 7th. Write it over 1. Take Q, write it over 1. You know that the numerators right here are the products. What do I have to do to get Q to look like KSP? Is Q larger or smaller than KSP? Well, you might have to think about this a little bit, but something times 10 to the negative 6th is larger than the KSP, which means I have more of the product than I would in KSP. Since I have more of the product, obviously I'll have more ions than needed to reach KSP, so a precipitate will form. If you don't like my explanation and you'd like to see more on this exact problem, check out page 754 in Brown-LeMay-Burston's 10th edition text, and you can see that exact problem worked. Let's look at some AP exam questions that use these ideas. We'll start with a few KSP questions, and we'll work forward from there. Here's last year's exam, or 2011 exam, depending on what year you're watching this. And it says, answer the question about the solubility reaction of the ionic compounds MOH and MCO, where CO3, where M represents an unidentified metal. Identify the charge of M. Well, CO3 is -2 and OH is -1, and there's 2 of them, so it's got to be +2. At 25 degrees Celsius, a saturated solution has a pH of 9.15. Calculate the molar concentration of OH minus in the saturated solution. So it's a KSP question, but they're asking you to do some stuff with pH. So you can find the POH then by subtracting from 14 and undo the log, and you end up with 1.4 times 10 to the negative 5th for the OH minus ion concentration. Write the solubility constant expression. So now we'd take for MOH2, dissociate it. Notice you get 2 OH minuses. So when you write the the KSP expression, make sure that you write OH to the second power. Calculate the value of the solubility product. Now, up here, you found the OH minus ion concentration. That's going to go in here. But how is the OH minus ion concentration related to M's concentration? Notice it's a 2-to-1 ratio. For every 2 of these, you get 1 of these. So I need half as much, and you can see they did half as much right here for M's concentration. You end up with 1.4 times 10 to the negative 15th. That's the KSP of this MSO4 thing. MOH2 thing. Next, they say, for the metal carbonate, the value of the solubility product constant is, and they give us a new solubility product constant at 25. On the basis of the information, your results from part B, which compound has the greater molar solubility? Justify your answer with a calculation. This is a great question. For MOH2, M plus solubility is 7 times 10 to the negative 6th. For MCO3, M plus 2 has a molar solubility of 2 times 10 to the negative 7th. Okay? You'll notice that the molar solubility here is taken from right up here, okay, because that's M's concentration in there. And then to find the molar solubility of M2 plus in the CO3, remember that the CO3 dissociates to form M plus and CO3 2 minus. And if you wanted to know the molar solubility, this would be X and this would be X because it's a 1-to-1 ratio. So it would be X squared is equal to the KSP, which is 7 times 10, 7.4 times 10 to the negative 14th. Square root that critter, and that's where you'd end up with the 2 times 10 to the negative 7th. Because 7 times 10 to the negative 6th is greater than 2 times 10 to the negative 7th, MOH2 has the greater molar solubility. So you look for the number that is larger, and that gives you the molar solubility. Turning to the back, let's see. This stuff decomposes at a high temperature. Some solid MCO3 remains in the container. The value of Kp is, right, the equilibrium constant expression. Notice for this one now, there's a gas in there and 2 solids. Don't put the solids in the Kp expression. Determine the pressure in atmospheres. So here's the pressure right here. Okay, this is the Kp, and you know Kp is equal to the pressure of the CO2. So easy one to calculate because it's already done for you. Indicate the G of the reaction. So this combines some chapter 19 stuff. G is equal to negative RT natural log of K. Plug that number in. G is positive, meaning that it's a non-spontaneous reaction. Let's look at another one. This is from 2006. Another solubility one. This one has PbI2. Gives us some info right here. Tells us the concentration of Pb plus 2 in solution. Tells us it's 1 liter. Write the equilibrium constant expression. Products. But don't put the reactants in there because it's a solid. Calculate the molar solubility. Okay. You can see that they tell us the concentration of Pb plus 2 in there. Okay. And they want to know the concentration of I minus in there. Notice it's a 2 to 1 ratio. So you need to take Pb's concentration, multiply it by 2. There you go. Calculate the value of the equilibrium constant. So now we take the concentration we got here, plug it in, the concentration from up here, plug it in, square that, because remember it's I squared. Okay, you got that up here. And then we get the KSP value. Easy schmeezy so far. Now, a saturated solution is prepared by adding PbI2 to distilled water to form 2 liters of the solution at 25 degrees Celsius. What are the molar concentrations of Pb plus 2 and I minus in the solution? Justify your answer. The molar concentration of Pb plus 2 and I minus would be the same as in the 1 liter solution in part 1. The concentrations of solute particles in a saturated solution are a function of KSP, which is independent of volume. So it doesn't matter whether you have 1 liter of the solution, 2 liters of the solution, 20 liters of the solution, the concentrations will remain the same. Now on the back, NaI is added to a solution of PbI2. Assuming that the volume of the solution does not change, does the molar concentration of the solution increase, decrease, or remain the same? Le Chatelier's principle. Notice we had some NaI. What's that going to be? Na plus and I minus. I minus is in common with PbI2. Okay? Therefore, you'll shift the equilibrium left because the PbI2 reaction will have more of this added to it, and it would adjust to reduce the stress by shifting left. The value of KSP in the salt of BaCrO4 is, when a 500 milliliter sample of this molarity of barium nitrate is added to 500 milliliter sample of sodium chromate, no precipitate is observed. Okay, so they gave us a KSP, they gave us 2 things that when added together would make this thing. See through that problem, see how that's working. Now, assuming the volumes are additive, calculate the molar concentrations of these guys. Now it's just molarity equals moles divided by liters. So we find the moles and divide it by the liters, and you get those molarities. Using the molar concentrations, show why precipitate does not form. You must show a calculation as part of this answer. So now they want you to find Q. So you plug those values in for Q, and you say Q is less than what KSP is, and therefore precipitate would not form. Hope you get one like that. That one's kind of an easy problem that it wouldn't be too bad for you to do. Let's take a look at another one. Now we're going to shift from solubility equilibria to a little bit of acid-base stuff. Propanoic acid, right here. This is from 2005, question number 1. Propanoic acid ionizes in water according to the following equation above, right? The equilibrium constant expression for the reaction. There's Ka. Then calculate the pH of 0.25 molar solution of propanoic acid. So here's a lose X, gain X, gain X one. We've got a nice ice table here. Ends up being a pH of 2.725. This is chapter 16 material right here. If you're struggling with this, go back and watch that video for a second. You can try this problem on your own. The back side, though, is the fun part. Now, here they say a sample of sodium propanoate is added to the propanoic acid. Assuming no change in volume, calculate each of the following. First of all, calculate the concentration of propanoate ion in solution. So we've got that sodium propanoate inside the propanoic acid, which means you're going to have to ice table the critter because you have a common ion. You have a common ion. Okay? So find your moles of each. Find your moles. Then take that. Divide it by the liters of solution right here. And here turns out to be the molarity of the propanoate ion in solution. Concentration of H plus solution has now been affected by having this stuff in there. Ice table it. You can see here's the concentration that you calculated up above right here. Here's the concentration that it started with way up here at the top of the question. You can notice how the question scaffolds on itself. Information here can be used way down here. Lose X, gain X, gain X. Assume it's small. Assume it's small. Solve for this X right here. X turns out to be 3.4 times 10 to the negative fifth. A great example of a common ion question. Methanoate ion reacts with water to form methanoic acid and hydroxide ion shown in the following equation. Given that OH minus in the solution method, calculate each of the following. They ask a bunch more questions there, and I don't have the rest of the question here. So they're going to ask you some stuff about this guy right here, and then they're going to add some sodium methanoate to it, so it's going to be a common ion right here. Great problem. Let's look at another one. This is 2005, Form B. Hypochlorous acid, weak acid in water. They give you the Ka expression and the Ka right here. Notice they write it correctly, HOCl. Write the chemical equation. Most challenging part of these, I think. Calculate the pH of HOCl. Hope you get one of these. This is really straightforward chapter 16 problem. Ice table. End up with a pH of 4.13. Write the net ionic equation for the reaction between HOCl and the strong base NaOH. Hey, now we're doing a titration. Okay? HOCl and OH makes them OCl minus. Watch out, watch out, watch out. H2O. Why do I say watch out? Because that's going to be a weak conjugate base, right? In an experiment, 20 milliliters of HOCl is placed in a flask and titrated with this much of NaOH. Calculate the number of moles of NaOH added. Molarity is equal to moles divided by liters, okay? Take your molarity times your liters. You end up with this many moles of NaOH added. Okay? Next part, we know the number of moles of NaOH added, so we could make an ice table of this, and it's coming. Calculate the H3O plus ion concentration in the flask after the NaOH has been added. So when in doubt, go to moles, especially in titration problems. Go to moles. So find your moles of HOCl as well. Here's your number of moles right here. We already know the moles of NaOH. Put them into the ice table. Okay? Here's the moles of HOCl. Here's the moles of NaOH. None to start with. Okay? Lose the one that's the smallest. Gain the one that's the smallest. 1-to-1 ratio right here. End up with some of this, some of this. What do you call a weak acid and its conjugate base that remains in the solution? Yep, if you said buffer, you're right. So now we got a Henry Hasselbalch that. They do it as another ice table. You could definitely use the Henry Hasselbalch end up with the pH, and then from that work backwards to get the OH3O plus concentration, which is 7 times 10 to the negative 9th. Okay? Calculate the OH minus ion concentration. Now it's just H plus OH minus is equal to 1 times 10 to the 14. And that's a nice, easy question after question number 2. So there's an example of a titration one. Let's do one more here. That's a titration one. This is from 2003, question number 1. Aniline, a weak base, reacts with water according to the following reaction above. See this little reaction right there? Write the equilibrium constant expression. Notice how lots of them start that way. Have you write that. Then a sample of aniline is dissolved in water. The pH of the solution is, calculate Kb. So now they tell you some information for the ice table. This is at equilibrium right here. So that's going to be at E of the ice table. Here is the concentration right here to start with. So plugging and chugging into there, you end up with 4.4 times 10 to the negative 10th for a Kb. Okay? Next part, a lot more fun once we get to the back. You're going to need that Kb on the back though. Okay? The solution is prepared as titrated with HCl. Calculate the pH of the solution when 5 milliliters of the acid has been added. Okay? Moles. Moles. Notice find moles of each. Then ice table those moles. What's left? Base, conjugate acid. Okay? Put it in the Henry-Hasselbalch equation. Put it in the Henry-Hasselbalch equation. They do a whole bunch more. Here's the Henry-Hasselbalch part right down here. Really small because it's really easy. End up with a pH of 5.24. Next, they want you to find the pH at the equivalence point for the titration. At the equivalence point, remember, the moles of acid are equal to the moles of base. So ice table, equal moles of acid, equal moles of bases. You end up with just some of this stuff left. What is this thing? Well, this is a conjugate acid, right? Conjugate acid then, take an ice table that critter, assuming gain x, x, x. You got to find the Ka from knowing the Kb and Kw. Then you can figure out what that is by doing the lose x, gain x thing, and you end up with a pH of 2.96. The pKa values of several indicators are given below. Which indicators are most suitable for the titration? Justify your answer. Now, if they give you a list of indicators with their pKa values, the pH at the equivalence point is acidic. The best indicator is erythrocyan, for which the value of pKa is closest to the pH at the equivalence point. Pick one whose pKa is close to the pH. All right, here's a Chapter 17 titration curve question. This is from 2010. They plunked a titration curve on the test, and then they asked you a bunch of questions about it. The first part was identify the solution that was initially added to the beaker. So since it's acidic right here, you should choose HCl. On the titration curve, circle the point that corresponds to the equivalence point. That better be in the middle right here. Middle of the steepest part. At the equivalence point, how many moles of titrant have been added? Well, we've got the volume right here, right? And it tells us that it is 0.1 molar NaOH. Multiply those two critters together, and this was a part of the test where you couldn't use a calculator, so 0.004. The same titration is performed again using an indicator. Use the information in the table below to select the best indicator. They give you a table below this that you can't see. Your best choice is methyl red because you want it to change somewhere in here. So choose an indicator that has a pH change somewhere in this steep part of the equivalence point. That's the end of that question. Last one. Here's one more that they give you a lactic acid structure. And then they want you to choose some equipment below to prepare a solution. Draw the Lewis dot structures here. Prepare a solution here. This is 2007 Form B if you want to go back and take a look at that. And then they ask some questions about a buffer on the back. 2 buffer solutions, each containing acetic acid and sodium acetate, are prepared. Student adds 0.1 moles of HCl to each of the buffer solutions. Table below shows the measurements made before and after. Write the balanced net ionic equation for the reaction that takes place. So you got to take And since you added HCl to it, that's H+, it'll add with the base of the buffer, and it'll make this guy. Explain why the buffer 1 is different from the pH in buffer 2, because HCl is added, each buffer had the same pH and thus had the same H+. Because Ka for acetic acid is a constant, the ratio of H+ to Ka all must be constant. This means the ratio of these is the same for both buffers, as shown by the following equation derived from the equilibrium constant expression. They go through a huge explanation there. Bottom line, take a look at how much the pH changed. For one of them, it changed a lot. For the other one, it didn't. Okay? So the reason that one changed a lot is because there's not a lot of conjugate base in the one, and the other one has a lot more conjugate base. As you can see, many AP exam questions contain stuff from this chapter 17. I encourage you to check out problem number 1 from lots of different years. Good luck with your chapter 17, Additional Aspects of Equilibria review.